Hello everyone, welcome back to my channel. This is Mira, and today we're going to be talking about cross-validation part 2. So if you watched the first part, we were talking about validation in general, and we were talking about why is it not the best approach. Today we're going to talk about cross-validation, so we're going to actually discuss what is cross-validation exactly and how to use it, and we're also going to have an example in Python to show you that. So let's get started. Alright, so in cross-validation, what we're going to do is basically we're going to divide the data into multiple different sets, and the main aim of cross-validation is to actually get to train the model on all of your data and not only a part of it, which was the main drawback of the previous approach. So I took this picture. I'm actually on scikit-learn website, and this is the part where they explain cross-validation, so I'm just gonna explain on that picture here. So basically here, this is just for like the diagram so you can understand. So when it's gray, this is all the data, and anything in green is going to be the training data, and anything in blue is going to be the test data. Let's just say that we're going to divide our data into different folds. And I'm going to explain in a bit what folds mean, but generally we use like the normal number of folds that you should use is either 5 or 10, and this is empirically. And basically if we choose 5 folds, then we divide all our data into different 5 folds, as you can see here, and each fold has the same number of observations. Then what we do is very simple. In the first time, we hold out the first fold. So the first fold is gonna be like set aside, and then we're gonna train the model on the rest of the 4 folds here. So the first fold is gonna act as our test set or validation set, and then the rest of the 4 other folds are gonna act as our training set. So we're gonna train the model on the green folds, and then we're gonna test it on the fold 1. And when we test it, we're gonna get an error, and we're just gonna say that this is the mean squared error for the sake of this example. Then in the second split, or the second loop, or whatever you want to call it, we're gonna hold out the second fold, and we're going to train the model on the rest of the 4 other folds. So all the green folds are gonna be used for training, and the second fold is gonna be used for testing, and we're gonna get another mean squared error. Then we're going to repeat this for all the 5 folds. So in each time we leave out 1 fold, we train the model on the other 4 folds, and then we test on this fold, the left out fold, and we get the mean squared error. And then at the end we get the average of all the different mean squared errors that we obtained, and then this would be our actual mean squared error. Now, what's interesting about this approach is that at the end of the day, we actually didn't lose any data that we haven't trained the model on. We have trained the model on all of the data, because each time we leave out a different set of observations. So at the end, we basically train on all of the observations, and we also basically test on all of the observations, which kind of a very good scenario. Okay, so back to the idea of the folds here. So basically you can change the number of folds to whatever you want, right? So we can make it 5, or we can make it 6, 7, all the way to 10, even more to 20, whatever you want. And I think the best thing to get to know which number do you want is by trial and error. So you can set the number of folds to 5 and try, and then see if you do it with 10. It also depends on like how big your data is. So another thing is leave out 1 cross-validation, which is basically, instead of the number of folds being 5 or 10 or whatever, we're gonna set the number of folds to n, where n is the number of observations in the data. So if I have 500 observations, then I will have 500 folds. So what does that mean? In terms of cross-validation, basically each time, I'm gonna put away one observation and train the model on the rest of the observations, n-1, and test the model on this one left out observation. So this is a very interesting approach because also we can kind of approximate the mean squared error by using another equation, but this is very, detailed and statistical, so we don't have to get into that right now. But basically, this approximate equation helps you to calculate the cross-validation error without having to actually run the model all these number of times, which is actually very time consuming, because imagine if you have a data of 1000 observations, you have to run the model basically 1000 times, which is a lot. So a good thing about this is that we have kind of an equation that approximates the mean squared error without having to do cross-validation. But the problem with leave one out cross-validation is that we're gonna have a very high variance. Why is that? Because the idea is that each time we're leaving only one observation out. So you can imagine the number of observations that are actually in the same folds. So imagine in the first split, we leave only one observation out. In the second split, we leave another observation out. But the number of observations in the first split and the second split that are common in both splits is a very big number, right? Most of them are the same. And so on in all the different splits. They are only different by one observation. So there's a huge correlation between the different splits that we make. And so we're going to have a very high variance because of that. But a good thing is that the leave out one cross-validation has actually low bias, because each time in each split, we're fitting the model to almost all of the observations in the data, right? So it's as if we're fitting the model to the whole data. So the bias is going to be really low, as opposed to when you use 5 folds or 10 folds or any number of folds, your results are going to be really biased, because each time you're actually, you have 4 or k-1 folds, and you're training the model on these number of folds when you're leaving out a complete fold, which would have observations that actually can change everything. So each time the results are going to be biased in favor to the folds that you have here. So this is the only difference. So it's more of a Bias-Variance Tradeoff, when you really don't want to have something that is really biased, and at the same time you don't want to have something that has a very high variance. So generally 5 folds or 10 folds are a really good number of folds for cross-validation. So now let's start our example.